Good morning, afternoon even. Welcome to Hunting Asynchronous Vulnerabilities. You may find it concerning that as you surf the web, scores of tidbits of information from your web browser are fed into hundreds of backend systems and processed, mangled, and data mined for all they're worth. Or you may think that's some serious attack surface. If only you had a way to harness it. In this session, I'll be sharing with you a range of techniques for mining invisible attack surfaces and finding vulnerabilities regardless of where they're hiding. Around 9 months ago, I was testing an online store, and there was a staging version of this store, but it was completely broken, so I had to test the live version. And as a result, I was being extremely careful not to enter any valid credit card details, because I didn't want to accidentally purchase a £1,000 leather jacket. And after spending the morning testing this, not really getting anywhere, I went out for lunch. And I came back to an interesting email. It said, "Dear James, congratulations on your purchase of that fine £1,000 leather jacket." And after the panic subsided and I realized that I couldn't have paid for it because I hadn't given them any credit card details, I realized I'd found a fairly serious vulnerability. I could potentially buy items for free. The only catch was I had no idea what had triggered this vulnerability. And the client probably wasn't going to be very happy when I walked up to them and went, "Hey there, I found this terrible vulnerability, but I can't tell you how to replicate it or how to fix it." It was only after 4 hours of reviewing my Burp Suite logs and failing to replicate the issue that I figured out that it was a session handling vulnerability caused by a conjunction of two events. I'd manually added a certain item to my shopping basket in the morning, and then the scanner had been running over lunchtime and had replayed a particular request which had triggered this vulnerability. So that was cool, and the client was fairly happy. But it left me wondering, what would have happened if there was no order confirmation email? Because in effect, that email was a callback from the application to me to let me know that it was vulnerable. And without that, I would have never found the vulnerability. Some random person might have got a leather jacket, but that would have been the end of it. And this issue of vulnerabilities lurking behind the scenes, where there's no direct output to the tester, doesn't just apply to session handling things. It can apply to SQL injection or OS command injection or pretty much any other vulnerability out there. And that sort of difficult to find vulnerability is exactly the kind of issue that can stay unpatched and lurk behind the scenes in production systems, which is the kind of vulnerability I like. So first, I'll talk about what the properties of these issues are that makes them so hard to find, and then look at a series of techniques that can be used to find them in a fairly reliable way and apply those techniques to some of the most major categories of vulnerability. Then I'll talk about what goes wrong, some of the hazards with these techniques, what can backfire, and finally take 5 minutes for questions. So the core issue is that many asynchronous vulnerabilities can be invisible. I'm using the term invisible here rather than blind because blind SQL injection means something completely different. Invisible here means you don't get any visible error messages, obviously. You also don't get any output that is influenced by your input. And finally, because they're asynchronous, there's no timing side channel, so you can't find the issue by injecting like a sleep kind of payload. And these can occur in various ways. The most common way, I think, is a blind issue that occurs in a background thread. So you could have a nightly cron job that's vulnerable to shell command injection, or even some kind of asynchronous task like sending an email that gets fired off straight away. You can also have event-triggered issues. So something like second-order SQL injection, where you've got your input on one page, but the vulnerable statement isn't executed until you perform a certain action on a different page. It's a well-known issue, but when it's blind, it can be really hard to find. Same for blind cross-site scripting. And finally, there are issues that aren't really asynchronous, but might as well be. So say you've got an application that takes XML input from you and parses it straight away, but doesn't give you the output. That might be vulnerable to an external XML entity include vulnerability, so you can read arbitrary files from their system, but without the ability to see the output, you can't tell if it's been successful or not. So how do we find these? Using callbacks. If we can send a payload that persuades something like a SQL server to connect to our server, then when that callback happens, that tells us we found an asynchronous stored SQL injection vulnerability somewhere in the application. And if we're careful about what payloads we send, like that connection can uniquely identify what the issue is. For this, we're going to use DNS, mostly because DNS generally isn't filtered outbound on networks, but it's also very convenient because most other network protocols use DNS. So say you've got a vulnerability like SMTP injection. You can blind carbon copy yourself on an email. You don't need to worry about implementing support for SMTP on your server because you'll get a DNS lookup first, and that's all you need to know. So that's the theory. It's pretty simple. Things get kind of challenging, however, when you try to look at each vulnerability and write a payload that causes this callback. It's easier in some technologies than others, but there's this core problem. When you're developing an exploit for a normal vulnerability, it's typically a fairly iterative process. You might throw a fuzz string at the application, see what error message comes back, and slowly and iteratively build up a payload that will do what you want to their server. Whereas with an asynchronous vulnerability, you will get no feedback from the application whatsoever unless your exploit works. So this means you have to walk up to the application with a payload that just works straight off the bat. So if you don't know whether the backend system where this payload ends up is on Windows or Unix, then you'll need to write a payload that works in both contexts. If you don't know where in a HTML page your input is going to be embedded, you need to write an XSS payload that works in any context. And similarly, it might be filtered, so you'll have to try and deal with that. And of course, you want your payload to be as simple as possible, because the more complex it is, the more things are going to go wrong. And you'll never know they went wrong. You just won't find the vulnerability. And if that sounds like a fairly tall order, then that's because it is. But it's worth it. So let's start off with something really simple that uses callbacks by its nature. So here, if you've got an application, let's say it's sending a password reset email, and a user has some kind of input that's being placed in the header of that email, they can potentially carbon copy themselves on the password reset email and hijack other people's accounts. And the email to the attacker here serves as a callback. Mozilla Persona had pretty much this exact vulnerability, but there was a bit of a catch, which is that the outbound mailer ignored all the headers that I injected. So what I had to do was use the header injection to attach a very well-known zip bomb onto this email that would lead to it being rejected by the recipient mail system and bounced. And then I could try to influence the place it got bounced to using the header injection to make it get bounced back to me. And that exploit wasn't too hard to build because I could see what was going on. But to exploit that in an asynchronous way, you would have just had to walk straight up with that exploit. So when building these exploits, it's crucial to try to anticipate everything that will go wrong in advance. Some technologies are really, really friendly to this method of hacking. This single XML document uses 6 different features of XML to issue a callback to my server. And we haven't had to try and chain any other vulnerabilities into it to get these callbacks. It's really simple. And the final 2 payloads are extra cool here because they don't need to be at the start of the XML document. They can appear anywhere inside an XML document. So if an application has a classic XML injection vulnerability, where they're simply taking user input and embedding it inside an XML document without encoding it, we can use those last two payloads to find that vulnerability in a reliable way that doesn't rely on error messages or anything like that. So these techniques have uses that go beyond finding purely asynchronous issues. Let's have a look at SQL injection. Here, the language SQL was not really designed with connecting to external services in mind. So we're going to have to look at each individual database and try and come up with a database-specific payload. With Postgre, I'm just doing these in order of how easy they are. The exploit is hiding in plain sight. I passed straight past the copy command and didn't notice anything that useful. And it was only when I came back to it that I saw this command actually lets you execute arbitrary shell commands on the server. So all we have to do is take a command like nslookup that works on both the Windows and Linux and write a SQL injection payload to trigger that. And we've got a callback that tells us this application is vulnerable to SQL injection somewhere in Postgre. Cool. What about SQLite? Here, there are a couple of functions that work on file paths. And Windows, like the underlying handlers, support UNC paths. So that's paths that can point to an external network device. So using these paths, we can easily trigger a callback to our server, but that's not going to get us anywhere on Linux. Microsoft have quite a few cool features that we can use to trigger pingbacks. Some of these have already been researched because triggering DNS lookups is useful as a way of exploiting SQL injection to get the database off the server and onto yours. However, as an asynchronous attacker, we've got more limitations than your standard one because we don't know what privileges our commands are being executed with. So something like OpenRoset isn't much use because it requires this config setting, and we don't know if we have it. Similarly, xbfileExist requires sysadmin privileges. We don't know if we have that. And bulk insert from with a UNC path also requires privileges that we may or may not have. Fortunately, there's this one other procedure, very similar to xbfileExist, xbdirtree. And this one requires sysadmin privileges officially. So if you try and execute that with no privileges, it will tell you this failed. However, at the point at which it tells you it failed, it has already done a DNS lookup. So we can use this to find Microsoft SQL injection in an asynchronous way with no privileges required for the database account whatsoever. Hopefully, that never gets patched. Oracle has quite a few features that you can use to trigger external lookups. If you want, you can write a payload for Oracle SQL injection that will send you an email describing the vulnerability, which is cool. But they all require various privileges, and once again, we want to avoid anything that needs privileges. Fortunately, in Oracle databases' many interesting features, it will parse XML. There's a built-in XML parser. And NetSpy found last year that this parser is vulnerable to XML external entity injection. And it doesn't require any privileges to parse XML. So we can kind of chain an XML injection, entity injection vulnerability in Oracle with SQL injection to trigger a pingback to our server that doesn't require any privileges. There has been a patch released for this, so if you're up against an Oracle DBA who studiously applies patches straight away, then it won't work. But it's worth a shot. Okay, one more SQL server. Let's have a look at MySQL. There's load file. Works, but only if the underlying operating system supports UNC paths. So it's Windows only. Select into out file is just the same, but it lets you write files, also Windows only. And by this point, you might have noticed that there's a reoccurring theme, which is that loads of these payloads only work on Windows. And by the time I reached this point in my research, I was getting really quite annoyed with this. And I thought, okay, what if I stop playing so nice and I say, okay, I'm happy to write files to the system to try and trigger some kind of side effect that does a callback? What then? So I'm going to focus on MySQL on Linux here, using select into out file to write arbitrary files. The obvious thing to do is to drop a web shell. There's a bit of a catch with this, especially from the point of view of an automated scanner like Burp Suite, which is that we don't know where the web root is, and so we're going to need to just spray shells over the server. And clients might not be too happy with that. Mail drops would be really, really useful if they worked. So some mail servers have a folder have a mail drop folder or a mail spool, where if you write a correctly formatted file, they will periodically grab that and email it off, which would be ideal. However, I could only get this to work on Windows. So it's useless because Windows supports UNC paths, which are easier. And by this point, okay, I was getting a little bit more desperate. All right, we've looked at mail spools. What about printer spools? So here, if we can write a file to a particular folder, it will be printed out somewhere. So what we need to do is get a payload like, dear employee, you have one employee of the month. To collect this reward, please email me at burpcollaborator.net. And obviously there's a bit of a catch. You need quite a gullible employee. And you also need root access to the system to be able to write to these folders on the Linux systems I tested. But on the bright side, it bypasses outbound network filtering. Okay, finally, here's something that is actually of use for you, but not for Burp Suite, for reasons you'll find out shortly. What if we try and write a config file? And in general, with this approach, it's best to target a config file for the vulnerability you're trying to find. So to find SQL injection on MySQL, I'm going to write a MySQL config file. MySQL's select into out file can't be used to overwrite files. But MySQL uses this strategy for loading files. It tries to load them from a number of different places, and it does this from the bottom up in that list, and it gives precedence to whichever one it hits first. So there's likely to be no file in the lower down locations, and we can write something there, and that will be used. And MySQL has a configuration option called bind address. And this defines the IP, or the interface, that when the server is next restarted, it will try to bind to. And it accepts the host name. So we can say, dear MySQL server, please bind to burpcollaborator.net. There's a little bit of a catch here, however, which is that pretty much regardless of what IP we return, it's going to fail to bind and the server will fail to start. And this could happen like several weeks after a test. It just happens when the server is next restarted. We can try to mitigate this slightly, because MySQL supports this string 0.0.0.0. It's like a pseudo IP address, and that means bind to all available interfaces. So we can make our DNS server return this IP, and then this server will bind to all available interfaces, and it will probably keep running. However, there's another way that could backfire. If their device has a private network interface and a public interface, it could bind to both, and then they might have some other issues. So most of the SQL and the XML payloads that I've talked about have been released into Burp Suite. The SQL ones are coming out in an update released now, but we haven't implemented that one. Okay, let's look at something where triggering a callback is quite a lot easier, so we can afford to take some other things into consideration. With command injection, we can use NSLOOKUP to easily trigger a callback. But we don't know what context our input is appearing in, whether it's on Unix on Windows, or what kind of quotes or lack of quotes might be encapsulating it. So what we'd like to do is come up with a payload that is quite simple, but yet will work in all of these contexts. And the key to doing that is a decent test bed. So this is just a web page I made that executes your statement in all of those contexts and tells you which ones worked. So here we can easily see with a really simple payload, we've got something that works in both of the unquoted contexts. And then we can simply use backticks to add Unix double-quoted context to the list of things that work without breaking anything else. So now we need to add support for single-quoted Unix. So we need to use single quotes to break out of that context and then just put one more single quote on to fix it again. And that just leaves Windows quoted. And this is the point where things get slightly trickier, because if we just put in a double quote to break out of the Unix quoted context, that will break, to break out of the Windows context, that will break the Unix payload, the double quoted one, right? Because the backticks will no longer work. Fortunately, Windows does not support escaping double quotes with backslashes, and Unix does. So if we inject slash followed by a quote, that will break out of that context on Windows only. So using an iterative technique, we've built up one payload that looks kind of complex if you look straight at it, but it was pretty simple to build. And it's reasonably short and will work in every context. Cross-site scripting is similar here. So it's really easy to trigger a callback in cross-site scripting if you know where you're appearing, but you don't know where within a HTML document your input is landing. And if you Google to find a solution to this problem, you'll land on a blog post by Gareth Hayes called One Vector to Rule Them All, which has this payload, which is a pretty cool payload, right? But it has a couple of issues for our use case. The number one, it's kind of obvious, it's too long. So if the input is being truncated, then that payload is very unlikely to work. It's also quite fragile. So in some contexts, it only works if you set window.name with the JavaScript you want to execute in advance. And it also uses quite a few special characters that may be broken by a filter and lead to the whole payload breaking. So I had a chat with Gareth Hayes and asked him if he could come up with something more suited to a pen test where the goal is to have something that executes as often as possible. And now I'm going to try to explain it. So to start with, we're just going to break out of any script context that we're in, if we can, and open an SVG or onload event handler to deal with direct injection. And now we need to deal with if we're landing inside a single or double quoted HTML attribute or a single or double quoted JavaScript string. So we do that, which works. And now we've reached a point where anything after this will be executed as JavaScript. So we just need to create a script and grab some information from the environment that will tell us like which line of JavaScript the vulnerable call came from, which will be useful in fixing it later, and append that script to the document. So that will import a full JavaScript file from evil.net. So that proves we've got proper arbitrary JavaScript execution. And this is cool because this payload is nice and short. And it also doesn't use much by way of special characters. So rather than using quotes here to make a string, we've just used regular expressions. So we only need forward slashes, which are much less likely to be filtered. And this payload will be used by Burp when we add support for this in the next month or two, hopefully. But if you're impatient, just last week, Netflix released a blind cross-site scripting framework called Sleepy Puppy, and you can just put that payload in that framework. Okay, there are some other issues, some slightly weirder issues that you might not look for on your standard web app test, because I'll just explain the issue. So let's say you've got an application, let's say it's called MediaWiki, and you can upload a file with an arbitrary name, but it has to end in .jpeg. And that gets written to a folder with that file name, and you can't break out of that folder. And it has to be a valid JPEG and all of that stuff, right? So by itself, that's not exploitable, as far as I know. But if there's a cron job or a studious sysadmin who happens to decide to back up all of the images and uses something like tar star, then we can exploit that. All we have to do is upload an image with a slightly suspicious file name. So what tar star will do when it sees that is it will interpret that as a command line argument, and it will execute that shell command and send a ping back to us to let us know we've got a shell somewhere. And there are variants of that payload that work for various other tools. Okay, so that's a fair amount of theory. Let's have a look at what this looks like in practice. So I'm going to take an application. It has a completely invisible attack surface, and it's fully patched. And I'm just going to throw some attacks at it and see what happens. So you know what happens. You get asked to test some brochureware website. And it's really boring. It's completely static content, and you can't do anything there. But if you look at what's happening in the background, you notice there's some kind of tracker, right? Just analytic software monitoring what you're doing. And here, regardless of what you send to this tracker, it just says 204 no response, right? So I can just put stuff in everywhere, and the chances are it will just say 204 no response. And we can't tell what's going on in the background. And sure, I can browse to the login page, but all that will tell me is that it's fully patched and I don't have a username or password. So you can try and guess passwords, but you can't really get anywhere. So what I've done is gone, okay, this is analytic software. They're probably interested in what Google search queries led people to that website. So I'm going to fake several Google searches leading me to this site using this prefix, and I'm going to put 3 different payloads in there. So far I've said it's really important that your payloads are like top class and work all the time. In this case, each of these payloads requires some user interaction. So I've just put 3 in there on the off chance that one of them will work. So let's have a look at what happens. So, okay, I've injected each of these payloads with these 3 requests. So the only difference between these requests is the payload, the fake referrer, and I've also changed the user agent on these so that POLYGLOT does not think that I'm the same visitor and then like merge them or not log them or something. So we finish our pen test and we've injected these payloads, and then at some point, with a bit of luck, some analytics person is going to wander on and log in. And it's not blind cross-site scripting, I'm sorry to say, but they're going to decide to export a spreadsheet. And if we're really lucky, they're going to open up the spreadsheet with LibreOffice or OpenOffice, missing a security patch or 2. And if that happens, then we're in luck because we've got a shell on their computer. So that's nice because, you know, okay, it wasn't the server that we were testing, but it's still a shell. And also, if they're logged on as an admin, they will, like at that instant, then we can easily, we've got a shell on their computer, we can hijack their session, we can use the admin to install a new module and get a shell on the server that we were actually supposed to be testing. Maybe we're not quite so lucky and they're using Microsoft Excel. Okay, so there's a couple of different ways this can go. Maybe they haven't had much security training and they make the critical mistake of reading this message. Because this message says, this could do something bad, do not enable this content unless you trust the source of this file. And what is the source of this file? Well, it's this analytics software that they kind of trust. So if they click enable, they get another thing with the same warning, open this if you trust the source of this workbook. And if they click OK again, then we get a show again. That's nice. That's not going to get patched, right? Because it's not a vulnerability in Excel. It's a vulnerability in PyWork. Finally, OK, what if they're a little bit more paranoid and they go, it's a scary security warning, and then disable? OK. They might then go, well, that was weird. I wonder what caused that. I'm just going to investigate. Oh, look, there's something weird going on here. And if they press that, then, oh, OK, I'm not connected to the internet, but I think you can see what happens. It sends a HTTP request to imgoingtohackyou.co.uk, which is my domain, and it leaks out some of the contents of the spreadsheet. So depending on what the spreadsheet is, we might get some sensitive stuff, but regardless of whether we get sensitive stuff or not, we've proven that application is vulnerable to Excel formula injection. OK. So that's enough about hacking stuff. What goes wrong? Quite a few things. Firstly, instances of what I would call friendly fire. Let's say burp scanner injects an Excel payload to get shell, and then a pen tester opens that spreadsheet. You know, we haven't really proved that there's a notable vulnerability because we've just exploited the human involved in the test, right? That's not that useful. Also, some applications may happen to grep inputs that they get for URLs and then fetch these to scan them for viruses or something. And that can create problems for us because take the XML injection payloads that we send, right? Those contain XML statements that have URLs in them. So if I pass this into Skype, say, and it fetches that URL, I might think Skype is vulnerable to XML injection when it really isn't. And finally, asynchronous payloads have got no concept of scope. I kind of touched on that with the demonstration, right? If you're assigned to do a 3-day test of a site, and then 2 weeks later you say, hey, I got a shell on one of your employees' computers, they might not actually be very pleased with that happening. So I think the key way to deal with that is just to provide payloads that don't execute shellcode or anything, they just do a callback. And hopefully that won't trigger too much instant response stuff. OK, so the key things to take away are asynchronous exploits fail silently. So the quality of the payload that you use is crucial. But ultimately, just because you can't see it doesn't mean you can't hack it. OK, I'll take 5 minutes of questions now. And then if you have any more, I'll be at the back, or you can send me an email. Don't forget to follow me on Twitter. Thank you for listening.